Okay, so let's get started. So I'll send you an email to remind you, but the final exam is this Friday. Uh, 12th of December. So the exam is at noon at USD in Old Main 204, which I think is the class for the lectures. So that means it's at 11 a.m. at the School of Mines. And at the School of Mines, it's in the classroom building, room 116. So it's not a DDN room, and Bai will be the proctor at the School of Mines. So I'd like to ask for a volunteer from the School of Mines to bring their laptop, and then we can do a Google Hangout to have a video connection between the two locations. That way, in case there's a question, you can ask me directly. So is there a volunteer that has a Gmail account at School of Mines that's willing to do that and bring their laptop to the exam, or a laptop? They'll all volunteer at once. All right. So how about both Daniel and Alex bring their laptops? That way we have a backup. And we'll set a Google Hangout, so maybe 10 minutes before the exam we'll make sure it works. Okay? All right. That way it's official. Okay. So I think that's all I have in terms of announcements. Any questions about that? As a reminder, you can bring 5 pages of notes. And there'll be a formula sheet provided that's similar in philosophy to the one that was provided during the midterm. And the format will be due 5 out of 6 questions. Okay. So if there's no questions for this review session, what I have planned is I will do a short review lecture covering all the material from the course, the important parts. And then I'll do 2 or 3 example problems that could highlight some of the things that we've seen in the course. And I'm happy to take requests at the end as well. Okay, so let's start with the review. So a high-level survey of what we did in the whole course, okay? So we seek to describe a system, and a mechanical system, classical mechanical system, And so we found that we can describe a system in either coordinate space which we call configuration space, or in phase space. To do that, we introduced what we called generalized coordinates, which we labeled typically QI. These generalized coordinates are used to specify all the particles in a system. We've considered systems that could be one or more particles, and so each of those particles can in principle have 3 Cartesian coordinates, x, y, z, or 3 spherical coordinates, r, theta, phi. And then each particle has its own 3 coordinates, and so the system itself is 3 times the number of coordinates times the number of particles, or the number of particles times 3, which is the number of coordinates. All right? And so specifying all those coordinates describes the system. We also introduced the generalized velocities, and those are simply the time derivatives of the QIs, which we denoted with a dot. And then we also introduced the generalized momenta, which were labeled as PI. So specifying the coordinates or the velocities and the momenta will specify the system at a given point in time. We found that we can figure out how the system evolves by finding the equations of motion. So the equations of motion tell us how the system evolves. And so in configuration space, we care about describing the functions Qi of t, and we found that this is given by a second order ordinary differential equation. In phase space, we give the time development of Qi and Pi of t, and this gives us 2n first order ODEs, where n equals the number of degrees of freedom. So that's very generally what we set out to do. So we found 2 ways of doing this. The first is the Lagrangian method. So in the Lagrangian method, you define what's called the Lagrangian, which is given by the kinetic energy minus the potential energy. And everything is based on this quantity L. Okay, so the equations of motion for each Qi, you get an equation of motion that's given by the Euler-Lagrange equation. And the Euler-Lagrange equation is d by dt of di-L by di-Qi dot minus di-L by di-Qi equals to 0. We'll call that the Euler-Lagrange equation. Now, we found that if the Lagrangian doesn't depend explicitly on time, so if you take the partial derivative of L with respect to t and you get 0, and we found that this quantity h, the Jacobi integral, which is given by the sum over I of Qi dot Pi minus L, is conserved. Okay, and this required us introducing the definition of Pi, which is di-L by di-Qi dot. That's the generalized momentum. So what does it mean for a quantity to be conserved? Okay. So for a quantity to be conserved, that means that the total time derivative of that quantity is equal to 0. That's what conserved means. It means it doesn't change with time. So to test if something is conserved, you take its time derivative, and if that time derivative is 0, then that quantity is conserved. And then we found a whole slew of methods that tell us if something is conserved. But ultimately, it's by equating the time derivative of that thing and seeing how it's equal to 0. Okay? So we should be careful. H is not always equal to the total energy. Sometimes it is, but sometimes it isn't. So H can be conserved with the total energy not being conserved. They're two different things. Okay? It can happen that H is equal to the energy. In fact, it's often the case that H is the total energy. But it's not always the total energy. And so just because H is conserved doesn't mean that the total energy is conserved. So just because di-L by di-T is equal to 0 doesn't mean that the total energy is conserved. It only means that H is conserved. We still have to show that H is the total energy. Okay? When we looked into symmetries, we found that if L is invariant, with respect to an infinitesimal transformation, where the transformation is given by, I replace all the Qi's with Qi plus Fi epsilon, and I replace all the T by t plus g times epsilon, where epsilon is small. So if you take the Lagrangian, you replace all the qi's by qi plus fi epsilon, all the t's by t plus g epsilon, and you find that the Lagrangian is unchanged, or at most changed by a total time derivative, then the quantity q, which is given by the sum over I of fi pi plus the Jacobi integral, which is the sum over I of pi qi dot minus L, is conserved. So again, that means that dq by dt equals to 0. Is there any delta? You could put a delta epsilon if you want here. That's just a notation. We're not strictly taking the variation of q with respect to epsilon. So what we're really saying is delta q equals fi times epsilon. So that allows us to make delta q as small as we want. So that would be the most correct notation. Let me just erase that. Okay. Any questions so far about the Lagrangian method? So most of the course has been demonstrating all this stuff, but these are the main results. Okay. So the second way of doing things that we looked at is the Hamiltonian method. So the Hamiltonian, h, is a function of the qi and the pi, and potentially t. Okay? And it's defined to be the Legendre transform of the Lagrangian. So it's the sum over I of qi dot pi minus L. And so you ask yourself, what's really the difference between the Hamiltonian and the Jacobi integral, which we just wrote? Well, the Jacobi integral, h, is still a function of qi dot, and t. So the Hamiltonian and the Jacobi integral are equal to each other. If you plug in numbers, you'll get the same number. But the Hamiltonian, we've removed the qi dots from the function, and we've replaced them by pi. So you have to go in, take what you have for the the Jacobi integral, and then you have to actually replace all the qi dots with the corresponding pi. And we've shown that it's always possible to do that. That's where we studied the Legendre transform, and we showed that indeed h is not a function of the qi dots anymore. It can be made solely a function of the pi. That was the whole point of the Legendre transform. Okay. So an important thing that we showed with the Hamiltonian is that the total time derivative in the Hamiltonian is equal to the partial derivative with respect to time of the Hamiltonian. Okay, that's not true for L. All right, the L by dt is not equal to di-L by dt in general. Sometimes it may be, but in general that would not be true. But for the Hamiltonian, it's explicitly true. So that means if the Hamiltonian doesn't depend explicitly on time, then the Hamiltonian itself is conserved. Right? Because if dH by dt equal to 0, since dH by dt is equal to 0 as well, then h must be conserved because its time derivative is 0. And just like before, capital H is not always equal to energy. Okay, so you have to be careful when you want to write out the Hamiltonian. You have to, if you really want to be safe, you should write it with the definition that we have above, not as t plus v. There's one more equation I forgot to write down. So we also showed in the process that di-L by dt is equal to minus di-H by dt. So again, if di-L by dt equals to 0, then di-H by dt equals 0, and dH by dt equals 0, then H is conserved. And that's really just like making the same statement as the Jacobi integral being conserved. Okay, any questions? So the equations of motion in the Hamiltonian framework are given by, very simply, Qi dot is di-H by di-P, and Pi dot is equal to minus di-Pi, sorry, di-H by di-Qi. These are called the canonical equations. All right, that's the equations of motion in the Hamiltonian framework. So they're very simple, and they're first order, and the time derivatives are on the left, and everything on the right doesn't depend on time. So in principle, they're simple-ish to solve. So we also looked at Poisson brackets. And they're particularly important because they have this connection to quantum mechanics. But you can also do all of classical mechanics using Poisson brackets. So the Poisson brackets of two functions, u and v, is defined to be the sum over all the coordinates I of di u by di qi times di v by di pi minus di u by di pi times di v by di qi. This should be 3 equal signs for a definition. Okay, so that's the definition of a Poisson bracket. So something very interesting that we found was that you can get the time derivative of some function, and that function, its time derivative, will be given by the Poisson bracket of the function with the Hamiltonian. And if that function depends explicitly on time, then there's an extra di u by di t. Yeah, question from Jason. Well, the short answer is the treatment of the Poisson brackets doesn't change at all. You're talking about a transformation that maybe mixes the first type and second type. Is that what you mean by two different types of coordinate transformation? Right, so ultimately, you end up being, you have to be able to write out, let me start from the beginning. The Poisson brackets, first of all, are independent of coordinate transformations, right? They're not, they come up a lot in canonical transformations, but they're an independent thing from canonical transformations. So at this point, what I've recovered in this review doesn't know about coordinate transformations, right? So this means you have a system of coordinates that you define, the q's and p's. You can always do that. And then you can calculate the Poisson brackets of two functions of the q's and p's, and all the algebra works out. Now in the case of a coordinate transformation where you have a Q1, a Q2, a P1, and a P2, and they go to a capital Q1, a capital Q2, and a capital P1, and a capital P2, that transformation might be dictated by some weird rules that mixes first and second type and third and fourth type transformations. But ultimately, you can write out the transformation equations. You can always write the capital Qi in terms of all the little Qi's and little Pi's, and same with the capital Pi's as a function of all the little Q's and little P's. So you can always write the transformation equations. It doesn't mean the transformation equations can be derived from a combination of types of transformation, but ultimately you have the set of equations that transform from one coordinate to the other. And at that point, you can evaluate the Poisson brackets between the transformed variables or the untransformed variables in terms of the other. Does that make sense? Yeah. Okay, so back to Poisson brackets. Very generally, forget the word canonical transformation for now. So we've defined this sort of abstract-looking and very annoying to calculate sum of partial derivatives. But then we found it has this nice property that the time derivative, total time derivative of some function u, can be calculated using the Poisson bracket. So that's very interesting now because if the Poisson bracket of u and h is equal to 0, and let's say u doesn't depend on time, then u is conserved. So this is a very powerful way of saying if some quantity is conserved. You simply evaluate the Poisson bracket of that quantity with the Hamiltonian. If that quantity doesn't depend on time and the Poisson bracket is equal to 0, that quantity is conserved, right? Because du by dt equals to 0, and if d by dt of something equals 0, something's conserved. Okay? Now with Noether's theorem, we saw that if the Lagrangian is invariant with respect to some transformation, knowing that transformation, you can then calculate a conserved quantity, which we called Q in the previous page. But sometimes it's not obvious what the connection between the transformation is and the conserved quantity. And so we showed that using the Poisson brackets, you can actually figure out what the coordinate transformation is that corresponds to that quantity being conserved. So if U is conserved, then you can get, say, Fx by taking the Poisson bracket of x in U, and this will tell us which transformation of x is the symmetry of L under which U is conserved. So that means that x prime would be equal to x plus the Poisson bracket of x in U, epsilon. And so that would be similar for all the other coordinates. And then the final topic is canonical transformations. So what is a canonical transformation? Well, the idea is that you go from variables qi and pi, lowercase, to a new set of variables capital Qi and capital Pi. So we've been writing the Hamiltonian in the M-transform coordinate as h of lowercase qi, lowercase pi, and t. And in the transformed coordinates, we've called it k, and k depends on the capital Qi and the capital Pi and t. And such a transformation, okay, slow down a bit, okay. So I thought, because I'm watching it on a separate laptop that's connected like a student, and today it was updating really fast. So if you need me to go back to the previous page, just let me know. I thought it was updating really fast today, so. Okay, let me go back to the previous page. If you want me to scroll up, let me know. Yeah, question, Michelle?
Yeah, when you're looking at the bracketed UH, the Poisson bracket, equals 0, do we have to also show them that the partial U dt is also equal to 0 in order for U to be conserved?
That's right, yes. But if U doesn't have any, doesn't like literally have the letter T in it, in the function that defines it, then it's trivial to show that dot U by dot T equals 0. So that's in general trivial to show.
Thanks.
All right, so back to the next page, canonical transformations. So the idea is to go from lowercase q and lowercase p to capital Q and capital P. So you can always do this, but we don't. This doesn't mean that the transformation is canonical. For the transformation to be canonical, it's canonical if the canonical equations, so on the left-hand side that would be that lowercase qi dot is di h by di pi, and lowercase pi dot is minus di h by di lowercase qi. It's canonical if those same equations are true in the transformed coordinates. So it's canonical if it's true that qi dot is equal to di k, by di capital Pi dot Pi, and capital Pi dot is minus di k by di capital Qi. Okay. So that transformation is only canonical if the canonical equations are satisfied in the transformed system and have exactly the same form. Okay? So that's simply what a canonical equation means. So we can guarantee the transformation to be canonical if we build the transformation so that the canonical equations will be satisfied. So we can do that so it's guaranteed if we write the transformed Hamiltonian, K of Q, capital Q and capital P, Qi and Pi, as H of lowercase qi and lowercase pi plus the partial derivative of some function, f, with respect to time. Okay, so we went through the exercise twice, actually, of doing this and then figuring out what given any arbitrary function f, what the transformation equations are back and forth between the lowercase and the uppercase variables, and that would guarantee that the transformation is canonical. So can choose an arbitrary f to define really an arbitrary Q and P and have a canonical transformation. So that's a really powerful statement. All right, so I have a Hamiltonian in a reasonable Q and P. Maybe it's Cartesian coordinates, so something very reasonable system. And I can make up any completely arbitrary function f, as long as it's continuous and stuff, but anything basically, and that will define a transformation to these new, in this case, completely arbitrary definitions of Q and P. They might not even have units of position and momenta, right? It's completely arbitrary. So we can redefine this physical system using completely arbitrary coordinates and completely arbitrary math. That's very powerful. That allows us to completely mess up what we mean by position and momentum. Right? Completely arbitrary coordinates. So one example of such a transformation, for example, we derived the canonical transformation of the first type, where f is a function of the lowercase qi and the capital Qi. All right, so we did an example of where for such a case where f depends on lowercase q and capital Q, the transformation equations are then given by the lowercase pi is given by diF, by di lowercase qi, and the capital pi are given by minus diF by di capital qi. So we introduce any function f that depends on the lowercase q's and the capital q's. Then you can define the p's and capital P's by diF by di q's, and then the transformation that follows from this is guaranteed to be canonical. So then we look at some properties of Poisson brackets and canonical transformations. So the brute force way to check if a transformation is canonical is to calculate the transform Hamiltonian, calculate the time derivatives of Q and P, and see if they're equal to what the canonical transformation, the canonical equation would give you. So is the time derivative of Q really di K by di P? Would be the really annoying way to evaluate whether a transformation is canonical. But we found a much easier way to test if the transformation is canonical. So you can test if it's a canonical transformation by taking the Poisson bracket of the capital Qi with the capital Pi, and that's got to be equal to delta Ij. So this is 1 if the Poisson bracket of Qi and Pj. So it's only equal to 1 if I equals to j, and 0 otherwise. And the other thing that you have to test is that the Poisson bracket of Qi with Qj is equal to the Poisson bracket of Pi with Pj, and that's equal to 0. That's the easiest test of a canonical transformation. So we also saw that when we evaluate these Poisson brackets, we can evaluate them in any coordinate system we want, as long as it's one of the canonical coordinate systems. So what's really important is that a Poisson bracket is what's called a canonical invariant. That means it's unchanged in value when evaluated in the lowercase Qi and Pi, or in the capital Qi and Pi. So you can take a Poisson bracket. So you have two functions of, let's say, u and v, and you write those functions in terms of the lowercase q's and p's. And then you calculate the Poisson bracket, and it's going to be a number. If you then re-express the u's and v's using the transformation equations in terms of capital U's and capital P's, and you calculate the Poisson bracket using the capital U's and the capital P's, you'll get the same number that you did when you did the lowercase q's and p's. So that's what canonical invariant means. That means you can calculate this Poisson brackets between the capital Q and the capital P to test if the transformation is canonical. You can calculate that Poisson bracket using the lowercase q's and lowercase p's, which often is the case if capital Q and capital P are given as functions of lowercase q and lowercase p. And that's the problem 3 or 4, I think, from assignment 4. Okay, you have to evaluate a bunch of plus-1 brackets between the variables. Okay. So recall, so we had that the new Hamiltonian K was given by H plus di F by di T, right? So the Hamilton-Jacobi equation is obtained from choosing F such that K is equal to 0. So this is a prescription for choosing the transformation so that the new Hamiltonian is identically 0. Now if the new Hamiltonian, K, is identically 0, then the capital Q and the capital P are constants of motion, because capital Qi dot is di K by di Pi, but K is 0. So capital Qi dot is 0, so Qi is a constant. And same with Pi. Capital Pi dot is equal to 0 because K is equal to 0. And so capital Pi is a constant. All right? So the Hamilton-Jacobi equation is obtained by making this choice, and it's an equation for the function f that gives us that special transformation. Okay? So call this choice of f S. So a specific case of f that gives h to be 0 is going to be called S. And in fact, we're going to use a transformation of the second type. So S depends on lowercase qi, capital Pi, and T. Okay? So I just plug this into our transformation equation with K equals to 0. Then I have H plus di S by di T equals 0. Okay, and that's the Hamilton-Jacobi equation. Now S depends on lowercase qi and capital Pi. But because K is constant, K is 0, sorry, capital Pi are constants. So I want to highlight that, and so I'm going to rename them. But capital Pi are constants, so call them alpha I. And then we also have for canonical transformations of the second type, the lowercase pi are given by di S by di Qi. Okay? So I'm going to rewrite S as a function of Qi, alpha I, and T, and I'm going to write the Hamiltonian H to be a function of the Qi, but instead of being a function of the Pi, it's going to be a function of the di S by di Qi and T. To highlight that I've gotten rid of the capital P's and made them constants, and that I can express the lowercase p's as a partial derivative with respect to S. So that means the Hamilton-Jacobi equation really should be written as the same thing, right? But I'll write out explicitly what everything depends on. So the Hamiltonian depends on Qi, di s by di Qi and t, plus di by di t of the function s, which depends on Qi, a constant alpha I, and t. So that's really the way to write out the Hamilton-Jacobi equation. Now we also saw that if the Hamiltonian doesn't depend explicitly on time, so if di h by di t equal to 0, then we can write this function s, which depends on Qi, alpha I, and t. It becomes separable, and we write it as a new function w that depends only on Qi and alpha I, and then minus some different alpha times t. That alpha there is usually equal to the total energy. So this function s, yeah, question? Sorry, yes, I forgot to say equals 0. Sorry about that. So we say that it's separable. If di h by di t equals 0, the function s is separable. So the equation above there, the Hamilton-Jacobi equation, that's a partial differential equation for s. S is a function of Qi and alpha I and t, and this is a partial differential equation. And typically the term di s by di Qi is going to be a di s by di Qi all squared, because that's what the pi is, right? And the momentum terms are usually squared in the kinetic energy. So this Hamilton-Jacobi equation typically will have a second order derivatives of s with respect to the Qi's and a first order derivative of the s with respect to t. And we saw it was very much like the Schrodinger equation. So this function s has a name and is called Hamilton's principal function. And w is called Hamilton's characteristic function. And then the last thing that we did is we introduced action angle variables. In particular, the action variable, which we labeled capital Ji, was given by the closed loop integral of pi dqi. That's over the period of motion of Qi. So we assume that the Qi's are periodic. So if that's the case, we can define these action variables J to be pi, the integral of pi. And then we saw that we can write the Hamiltonian as a function of the Qi, the capital Ji, and t. So in effect, this corresponds to a canonical transformation where the transformed canonical momenta, the capital PI's, are these JI's. Okay, so then we found we could write the Hamiltonian in terms of these JI's. And the important result we found was that the frequency mu I that was associated with the period of the motion Qi was given simply by the partial derivative of the Hamiltonian with respect to that action variable. So that was a rather complicated mathematical result, but it allowed us to find out the frequency of a motion without actually having to solve for the motion. All we have to do is do some transformations to the Hamiltonian and then take a partial derivative of the Hamiltonian, and that gives us the frequency of the motion. If you really wanted to find out the frequency of the motion for a simple harmonic oscillator from first principles, you have to solve the second order differential equation to get, in this case, a sine function for the oscillation of a simple harmonic oscillator. But you have to solve the second order ODE, equation of motion, to get the actual function to find out what its period is. So this removes the need to actually solve the equations of motion to get the frequencies. Okay, and then we saw that in some of the old school quantum mechanics, like the Bohr atom, they're the really first stuff, is actually based on quantizing these action variables. But the more modern way of doing quantum mechanics depends on the Poisson brackets and converting the Poisson brackets to commutators. Okay, so that's the whole course in a few pages. Any questions? So when you're studying, you should make sure you understand all the why these things are all true. Okay. So there's still a mistake in the notes. Is that the part where it has a mistake? So I don't know by heart what equation 5.4 and 5.7 are, so I need to go look them up. Can I talk more about continuous transformations? Yeah, so equation 5.7 is a little bit tricky. So equation 5.7 was that Qi primed is equal to Qi plus delta Qi plus Qi dot delta t plus second order terms. And that allowed me to write that delta Qi primed was defined to be delta Qi plus Qi dot delta t. Okay, so originally we defined the continuous transformation Qi prime to be Qi plus delta Qi, and we defined t primed to be t plus delta t. Okay, so this Qi primed we can write as Qi plus some function of the QIs times epsilon. So that allows me to vary QI by a little bit by having this function f that depends on the QIs, and then this epsilon, which I can make as small as I want. Okay, so that's sort of the basic definition from variational calculus of what a variation is, right? It's the varied QI, which I'll call QI prime here, is QI plus some function that I can make arbitrarily small. Now, in Noether's theorem, we consider the case where we make a variation not only of the QIs, but simultaneously of the delta T's. So that's exactly what's going on. Yes, it depends on T. So what we did in Noether's theorem is more like saying that this was equal to QI plus some function that depend on the QIs and the T's times epsilon. And so that's why ultimately we end up writing in this form. So then we just do a Taylor series expansion and we collect the terms that are the lowest order. And 5.4. Yes. So in 5.4, when I explained it, I sort of conceptually explained it with T being held fixed, but in principle T can also be varied, which is the case we need for Noether's theorem. But to be honest, because the derivation didn't work so well in class, I actually won't ask any questions on it. So I have to say this whole part of, that's the only, well actually the only part of the course. These couple steps here are a little bit wishy-washy. Normally Noether's theorem is done for a continuous case, which I had to modify here. Okay. Any more questions? Or does that answer your question enough? Okay. So I wanted to finish the today by solving a couple problems. So I guess we're almost near the end of the time anyway. So yeah, I'll be in at USD on Wednesday, Lou, if you want to drop by my office. Yeah, so let's do a couple of problems. If you can do these problems, then you're probably okay for the exam. All right, so let's do an example where we have a hemispherical bowl. Okay. And inside this bowl we have a sphere. So this bowl has a radius capital R. We have this little sphere in here. Oops. And it has a radius lowercase r. Let's say that the sphere is located at an angle theta, and it has its own little angle phi. And I'm going to put a coordinate system at the center of the bowl. Okay. So this is a sphere. And let's say rolling without slipping. Along a hemispherical track. Okay. So it's a ball, and it's constrained to roll around this two-dimensional track that's shaped like a bowl or a circle. Okay. And let's do everything. So let's find L, equations of motion, H, canonical equations, and conserved quantities. Okay? So any questions about the physical problem, what it looks like? All right, so we'll start with L, because everything always begins with the Lagrangian. So I want to specify the Lagrangian, I need to know the kinetic energy and the potential energy. And before that, I need to know how many degrees of freedom. So first question, how many degrees of freedom? So it's rolling without slipping, so it's only 1 degree of freedom. Right? I just need to specify theta. So we have 1 degree of freedom, and I'll call it theta. So it's immediately apparent that if the ball is rolling, it's going to have some moment of inertia, and so we need to know how fast it's rolling to calculate its rotational kinetic energy. So we need to relate theta to phi, because phi dot is going to be the term that has the rotational kinetic energy. So we have a constraint that capital R times theta is equal to lowercase r times phi. So that means that phi dot is given by big R over little r times theta. Now, to describe the motion of the system, I need to know its position of the ball, which I can specify by theta, but I need to know its translational kinetic energy, which is easier to calculate in Cartesian coordinates, x and y. So I need to know how x and y of the ball relate to my generalized coordinate theta. So more importantly, I want to know how the center of mass position of the ball, which I'll label x and y, how it depends on theta. Because I need to know the position of the center of mass to know the potential energy. So yes, it was theta dot. Phi dot is r over r theta dot. Sorry about that. So with my coordinate system of x going to the right and y going up and centered at the origin of the bowl, then I can write for the sphere center mass position, x is given by capital R minus lowercase r times cos theta, times sine theta, sorry. And y is given by minus r minus r cos theta. Okay, so y is negative here, right? And just because I'm going to have a lot of r's minus r's, I'm going to call L I'm going to introduce L to be capital R minus lowercase r. Just so I don't have to write r minus r everywhere. Okay. So that's the position. So generally we're interested in the velocities. So x dot is given by dt of L sine theta. So that's going to be L cos theta, theta dot. Y dot is going to be L sine theta, theta dot. All right. So that means the term that I need, which is going to be x dot squared plus y dot squared, that's going to be equal to L squared theta dot squared. Okay? So the kinetic energy, T, is a half m times x dot squared plus y dot squared plus a half I omega squared. So in terms of our generalized coordinates, that's a half m x dot squared plus y dot squared I just wrote, so that's L squared theta dot squared, plus a half. So the moment of inertia for a sphere is 2/5 m lowercase r squared. And then omega, which is phi dot, right? That's equal to, since it's omega squared, so I have capital R squared, lowercase r squared, theta dot squared. So V, the potential energy, is equal to mgy, right? So I have y pointing up. So potential energy is just given by mgy. Now if I plug in my formula for y, that's minus mg L cos theta. Right? Remember, y is minus L cos theta. So the potential energy, because y is pointing up, is plus mgy. But then in terms of theta, I have a minus sign in there. That's simply because of my definition of theta and y. Okay. So now I have everything I need, so I can write L equals T minus V. So I can write out the Lagrangian, L. So the T is a half m L squared theta dot squared. If I simplify this second term in the kinetic energy, the lowercase r squares cancel, and the two cancels. So I'm left with plus a fifth of m capital R squared theta dot squared. And then minus the potential energy. The potential energy is minus mgl cos theta. So plus mg mgl cos theta. Yeah.
So your y is in a negative direction. Gravity is in a negative direction. How did we end up with a negative potential energy?
Well, so look at our diagram here with the coordinate system x and y. All right, so if I put a particle up here, where I drew this blue star. All right, so you agree that gravity is down. All right, and the potential energy of this thing here sits at a height h. V equals mgh. So in general, V equals mg times the y coordinate of a thing. Right? If y is pointing up. If y is pointing down, it would be negative, but y is pointing up, so the potential energy of things is mgy. Now if I take the thing and I put it below the x-axis, then its potential energy is still mgy, but y is a negative number. So if I write out the expression, it'll be, minus mg times 2 meters. So here the expression for y is negative because the ball is below the x-axis. All right, so my expression for y has a minus L cos theta in it. So V is plus mgy, so it's mg times minus L cos theta. So that's V. So plus V is minus mg L cos theta. And then when I subtract the V from the Lagrangian, then that becomes a plus. Okay? So it's very easy to get mixed up. But if y is pointing positive up, then potential energy is plus mgy. And then if your thing is below the x-axis, then it has a negative y. That's just the way it is. Okay? So we have our Lagrangian. So we can now calculate, let's say, the equations of motion, or equation of motion, since there's only one generalized coordinate. So to get the EOM, we need dial by di theta dot. So dial by di theta dot is, from the first term, it's ml squared theta dot. And from the second term, it's 2/5 m capital R squared theta dot. We also need dial by di theta. So the only term that depends on theta is the last term. So that's going to be minus mgl sine theta. And now the Euler-Lagrange equation is d by dt of the dial by di theta dot. So if I take d by dt of our expression here for dial by di theta dot, the only thing that's not constant is the theta dot. So they just transform into theta double dots. So I end up with, I'm going to factor out ml squared plus 2/5 mr squared, theta double dot. And then it's minus dial by di theta. So it's plus mgl sine theta, and that's got to be equal to 0. Yeah, I'll try to get the review posted. It takes them a while to convert the video. The notes will be up right away, and then the video itself might be a while. Okay? But yeah, I'll go through the whole derivation for the whole problem. That way, I highly recommend that you guys go through the problem as I solve it. I think it's probably helpful for you guys. So please review even the video. I highly recommend you review the video before the exam. Okay. All right, so there's our equation of motion. And then we can pretty it up a little bit. You see each term has an m, so the m's cancel. Now let me just put it in a familiar form, so let's keep theta dot on the left. And on the right-hand side, we're going to have a minus L over L squared. It doesn't like to write it there. I'm going to start a new page here, sorry. The tablet doesn't like when I write at the bottom of it. Alright, so new page. So I put everything together. I have theta double dot equals minus L over L squared plus 2/5 capital R squared G sine theta. Okay. So this is very much like a simple pendulum with a weird value of L. But what happens is the ball is going to oscillate at the bottom of the bowl because it looks almost exactly like a simple pendulum equation. So note, for example, if big R is much, much bigger than little r, then L is roughly equal to R, big R, right? Because L was big R minus little r. So if big R is much, much bigger than little r, then L is roughly equal to R. And so in that case, theta double dot is roughly equal to minus R over R squared plus 2/5 R squared G sine theta. So that's equal to 5 over 7R, minus 5 over 7R G sine theta. So that's like a pendulum where the length is given by 7/5 of R. Okay, so that's one more thing, I guess, is before we look at the Hamiltonian, any conserved quantities. So our Lagrangian L was given by, go back and look, half ml squared theta dot squared plus 1/5 mr squared theta dot squared plus mgl cos theta. So that's all Lagrangian. So any conserved quantities. So there's no cyclic coordinate. So no conserved momenta. However, di-L by di-T equals 0. So we expect the Jacobi integral H to be a constant and to be conserved. So let's evaluate H. So we need Pi, which is di-L by di theta dot. So instead of calling it Pi, let me call that P theta. So we already did di-L by di theta. Di-L by di theta is mL squared theta dot. So it's di by di theta dot plus 2/5 mR squared theta dot. So the Jacobi integral, right, that's given by the sum over I of pi qi minus L. So if I evaluate h, so the sum over I, there's only one generalized coordinate. So it's p theta theta dot. Sorry, it's qi dot. So p theta theta dot minus L. So p theta is what we just have here times theta dot. So that's m L squared theta dot squared plus 2/5 m r squared theta dot squared minus L, so minus 1/2 m L squared theta dot squared minus 1/5 m r squared theta dot squared minus mgl cos theta. So if I simplify this, I have ml squared theta dot squared minus 1/2, so they're the same thing. So I'm left with 1/2 ml squared theta dot squared plus 2/5 minus 1/5, so plus 1/5 m r squared theta dot squared, and then minus mgl cos theta. So if I compare this Jacobi integral, which we know is conserved, to the Lagrangian, I can see that indeed actually it turns out that h is equal to t plus v. So in this case, that conserved quantity, which I've written out explicitly, turns out to be the total energy. Okay. That's it for conserved quantities. Now, let's do this whole thing with the Hamiltonian and see if we get the same equation of motion. Oh, okay. Copy. All right. So let's do the whole thing now with the Hamiltonian. So I copied down our Lagrangian there. So the Hamiltonian H is given by p theta theta dot minus L. All right. So we just literally just calculate that for the Jacobi integral. So let me write it out as the Jacobi integral. So that's equal to 1/2 ml squared theta dot squared plus 1/2 m r squared theta dot squared minus mgl cos theta. Right? At this point, that's still the Jacobi integral. That's technically not the Hamiltonian because we have theta dots in there instead of p thetas. All right, so we need to remove the theta dot squareds. So we have to use the fact that theta dot, let me just rewrite the equation that we had before. So p theta was equal to ml squared theta dot plus 2/5 m capital R squared theta dot. Okay, so that's p theta. So we have to write that out as how to write theta dot in terms of p theta. So from that, we can find that theta dot is equal to p theta times 1 over ml squared plus 2/5 mr squared. All right. So if I put that into our expression for the Hamiltonian, so h of theta and p theta, so that's a half m L squared and theta dot squared. Theta dot squared now is p theta squared over ml squared plus 2/5 mr squared plus 1/5 mr squared times p theta squared over ml squared plus 2/5 mr squared. Squared. Forgot to say the squared on the bottom parenthesis there. Minus mgl cos theta. So we can make this a little bit prettier. We can add these two terms together by putting them on the same common denominator. So that's equal to a half m, and factor out the p theta squared. No, without the half. So the two terms are the same, right? The denominators are the same, except the first term is 1 over 2 times ml squared plus 2/5 mr squared. And the second term is 1 over 5 times ml squared. So if I'll make them the same denominator, I have to multiply the first one by 5 and the second one by 2. So then they're over 1 over 10. And then the first term is 5L squared plus 2R squared. And the denominator at the bottom, I'm going to pull out an m squared. And then I'm left with L squared plus 2/5 R squared squared. I think that's correct. So I'm going to cancel the m at the top with the squared at the bottom. And the 10, I'm going to factor into 2 times 5. Or I'm going to keep the 2 out front, and I'm going to bring the 5 inside the square bracket. So I'm left with 1 over 2m p theta squared. And that whole term in bracket now evaluates to at 1 over L squared plus 2/5 R squared. So I bring out of the 10, I break the 10 into a 2 and a 5. 2 I left at the front with the 1 over 2m. And the 5, I divided the numerator. So the numerator divided by 5 is L squared plus 2/5 R squared. And that L squared plus 2/5 R squared cancels one of the squareds that's at the bottom. At the bottom I have L squared plus 2/5 R squared all squared. So the numerator cancels one of the bottom ones. And so that's what I'm left with. Okay? So that's their Hamiltonian. So the first line was okay for the Hamiltonian, but of course the last line is a little bit prettier. So now the Hamiltonian doesn't have any theta dots in it anymore. Yeah. So now, do we get the same equation of motion that we did before? That's the question. So let's do the equations of motion from the canonical equations. EOM from CE, canonical equations. So the first canonical equation is that theta dot is di h by di p theta. So if I do di h by di p theta, h is the thing that I have just above here, then I get p theta over m times 1 over L squared plus 2/5 R squared. All right, in the second term, the minus MGL cos theta doesn't depend on p theta. So that's the differential equation for theta dot. And now the differential equation for p theta dot is minus di h by di theta. So in h, only the second term depends on theta. So if I do, so the second term is minus, so again, I was going to confuse you with the signs here. That term is minus MGL cos theta. So if I do d by d theta of that, then it's plus MGL sine theta. But p theta dot is minus that derivative, so it's minus MGL sine theta. I believe that's correct. Okay, so how do we compare that to what we had before? Because before we actually had an equation for theta double dot, not theta dot. So we want to compare with the equation for theta double dot. So how do we use these two equations to get the equation for theta double dot? So the equation for theta dot, it's p theta over m times that. And we have an equation for p theta dot. All right. So if we want an equation for theta dot double dot, we have to use the fact that theta double dot is d by dt of theta dot. So I have to take d by dt of my equation for theta dot. So if I take d by dt of my equation for theta dot, the only thing that depends on t is p theta. Everything else, 1 over m and 1 over L squared plus 2/5 R squared are constants. All right. So if I do d by dt of theta dot, then I get 1 over m, 1 over L squared plus 2/5 R squared times p theta dot. And p theta dot I have in the second expression. So So if I plug that in, now you see when I plug in the p theta dot, the m's will cancel. So I'm left with L, or minus L, over L squared plus 2/5 R squared G sine theta. As we did from the Euler-Lagrange equation. So that's good. Okay, so here's a sort of example fully carried out, both the Lagrangian and Hamilton, and I had two terms for the kinetic energy because there's a rotation. And then we found the same equations of motion with Hamilton and Lagrange methods, as well as the conserved quantities. Okay. I want to do a couple notes. I'm not going to carry you through the problems in their entirety because we've already done this. But just so you think about it. So recall the problem of our pendulum So we have a pendulum with a moving fulcrum. And we have gravity down. Okay? So consider the problem of the pendulum with the fulcrum moving at constant speed, let's say in the positive y direction. Okay? So how to solve this problem? So if we do it with the Lagrange method, right, first you need to write the x and y positions of the mass. And we only have one generalized coordinate, theta. 1 degree of freedom. Let's call it theta. So the x-coordinate is given by L sine theta. And the y-coordinate, if the fulcrum started at t equals 0 at the origin, it's equal to v times t minus L cos theta. So that means that x dot is given by L cos theta, theta dot, and y dot is equal to v plus L sine theta, theta dot. Okay. I wonder what that one is about. All right, so now if we want to write the Lagrangian for the system, we write t minus v. So t is equal to, so if you do the x dot squared plus y dot squared, you find that t equals a half m. And then we're left with L squared theta dot squared plus 2VL sine theta, theta dot plus V squared. And then V, which is equal to mgy, it's equal to m. So again, y is in the positive direction, so v is plus mgy And so it's mg, and what we have for y is vt minus L cos theta. So question, is energy conserved? The answer is no, right? It's very obviously no because L depends on T, the Lagrangian. I guess it's always awkward when I keep calling the length of the pendulum capital L as well as the Lagrangian. Okay, so the Lagrangian L, which is T minus V, is a half m L squared theta dot squared plus 2VL sine theta, theta dot, plus V squared minus mg times Vt minus L cos theta. So in this case, di L by di T is equal to minus mgv. So not equal to 0 unless v is equal to 0. So the Jacobi integral is not constant. Okay, so maybe that was obvious. Let's try a slightly different case. Can I change page or do you need a second? Okay, so let's do another one. Let's do the same thing again. Now we have the same pendulum. Let's call it lowercase l for less confusion. Theta m x and y. But now we have the fulcrum moving with v in the plus x direction. Okay. So same thing, you would write that x is now equal to vt plus L sine theta. Y is minus L cos theta. So x dot is v plus L cos theta, theta dot. Y dot is L sine theta, theta dot. So T is equal to a half m, so I'm going to have L squared theta dot squared. And then I'm going to have plus 2V L cos theta, theta dot, plus V squared. And V, which is mgy, that's just going to be minus mgl cos theta. Okay? So it's the same thing. It's a pendulum and it's going, the fulcrum now is moving in the y direction, in the x direction, horizontally. So is energy conserved? Well, I should write out L as T minus V. you'd be tempted to say, well, there's no t's in here, so diL by dt is equal to 0, and so energy must be conserved. But remember my words of caution earlier is that the Jacobi integral is conserved. That doesn't mean the energy is conserved. So we should see if the two really are equal. Okay. So L equals T minus V, so it's half M L squared theta dot squared plus 2VL cos theta theta dot plus V squared. In principle, the term half M V squared is a constant, and so it doesn't influence the motion, so it could be removed. Minus, so it's T minus V, so then it's plus mg L cos theta. So clearly, diL by dt equals to 0. So h is conserved, lowercase h. So let's evaluate lowercase h. So to evaluate lowercase h, I'm going to need p theta. So we need p theta, which is diL by di theta dot. And diL by di theta dot is mL squared theta dot plus mvL cos theta. Is that right? So if we evaluate h, so that's p theta times theta dot minus L. So if I do p theta times theta dot, that's mL squared theta dot squared plus mvL cos theta theta dot then it's minus a half mL squared theta dot squared minus mvL cos theta theta dot minus mgL cos theta. All right. So we have here the mvL cos theta theta dot term actually cancels when you calculate lowercase h. So I'm left with, so I have an mL squared theta dot squared minus half mL squared theta dot squared. So I have a half mL squared theta dot squared. The cross terms cancel, and then I have minus mgL cos theta. Yeah. That's right. Sorry, I should also have minus a half mv squared minus a half v squared. That's right. Subconsciously knew it didn't matter. But thanks for pointing it out. Okay, so now compare L and H. So T plus V is simply L, where the last sign becomes mgL cos theta, that's minus mgL cos theta. So that part worked. But the kinetic energy part did not work, right? In the kinetic energy, there's supposed to be a cross term of theta dot and V's. And that's canceled out of the Jacobi integral. Okay, so this term here hardly matters, but it also changed between the two terms, right? Between L and H, the half mv squared changed sign, and there was nothing to cancel it out. But since it's a constant, I could have ignored it in L, and then you wouldn't have noticed it make a difference. So clearly in this case here, H is not equal to T plus V. But H is conserved. Just to be patently clear, total energy is not conserved. So here's a case that's actually quite simple, where di-L by di-T is 0, so H, lowercase h, is conserved, but it's not equal to the energy. So the energy in this system is not conserved. So does that make physical sense to you guys? Did you have a question, Lou, or I don't know what the red X means? Or was that a voting thing? That was a voting. Nice. Oh, you have Lou, you have like a red X next to your name. Anyway. Okay, so why is it not conserved physically? So there's clearly a motor. So think of the fulcrum as a separate mass, right? So you can think of the fulcrum as a mass where the cable is attached, where M can swing about. So if you don't touch the system, while M swings, let's say in the diagram we have now, let's say M is falling, so M is going to swing to the left. There's going to be a reaction force, if you will, on the top fulcrum that's going to push the fulcrum to the right. And then when M starts swinging the other way, the fulcrum will swing the other way. So that's the natural way it would behave if it conserved energy. So the center of mass of the system would be fixed, or moving at constant speed. But the top fulcrum would be moving back and forth to compensate for the motion of the mass at the bottom, if the fulcrum had a mass. But we're not letting that happen. In fact, we're forcing the fulcrum to move at a constant speed v. So we're inputting energy to the system because we're not letting the fulcrum swing back when the mass wants it to swing back, or we're not letting it accelerate it to the right when the mass is trying to accelerate it. So because of that, energy is not conserved, because you're not considering the whole system. There's clearly a motor involved to keep the fulcrum moving at a constant speed. The fulcrum, under the reaction forces that it experiences, does not want to move at a constant velocity. It wants to keep accelerating back and forth. Okay? So it makes sense that energy is not conserved because we're not considering the whole system. Now if you let the fulcrum be free, and you model it as a second mass that's constrained maybe to move in the x direction, then energy is conserved. And then you would find that the center of mass of the system is fixed. Now the quantity that's conserved, H, is in fact the total energy of the system if V was equal to 0. So if V was equal to 0, so it was like a vanilla pendulum, then energy is conserved. And so that requires V to be equal to 0. And then that makes sense. So it all makes sense now, because this pendulum in our problem here with the moving fulcrum, the equation of motion that you get will still be the same. Right? You're still going to get theta double dot equals minus G over L sine theta. You're going to get the same equation of motion, because moving the fulcrum at a constant speed is like looking at the system in a different frame of motion, in an inertial frame of reference. So you still get the same equation of motion that's independent of the frame of reference. But the total energy depends on the frame of reference, right? Because the speed of something in one frame of reference could be 0, and another frame of reference is not 0. Because you need, for the kinetic energy, right, you have mv squared. So because of that, energy is not conserved in this moving frame of reference. Okay? So it's important that you understand this, and this a very simple example where h is not equal to t plus v, yet it's conserved. And so even though the equation of motion is exactly the same as a fixed pendulum, and energy is conserved in a fixed pendulum, in this particular problem it's not conserved because you're not in the same frame of reference as the fixed pendulum, where you would define the energy. Okay? So I have one more problem, and this is the Hamilton-Jacobi problem. All right, so I figured the first problem really covered conserved quantities, and this little aside helped with conserved quantities. In the first problem, we also did a Hamiltonian, and we went from how you go from the Lagrangian to the Hamiltonian, how you get the equations of motion, check that they really are the same equation of motion between one system and the other. And so the technique just generalizes to all these problems. So there's not much to it. So the Hamilton-Jacobi, we really have not had much practice. So there's one example in the notes. So let me give you a more abstract example of applying the Hamilton-Jacobi equation. Okay? And this will be the last example for today. Because this is a long lecture. Okay, so say we're given a system, and we know that the kinetic energy T is given by a half, and this is going to look funny, Q1 dot squared plus Q2 dot squared times Q1 squared plus Q2 squared. And the potential energy V is given by 1 over Q1 squared plus Q2 squared. Okay, so that's given. All right, so there's 2 degrees of freedom, and T plus V are known. Okay, so for the system, let's find L, the Lagrangian, H, the Hamiltonian, and the Hamilton-Jacobi equation. Okay? So it's a purely abstract system. We have no idea what the physics are. We just know that the mathematically you can describe with a kinetic energy term that depends on 2 degrees of freedom, and a potential energy term that also depends on those 2 degrees of freedom. So we have Q1, Q2, Q1 dot, and Q2 dot. Okay? So step 1, write out the Lagrangian for the system. That's trivial. So L is given by T minus V. So I'll just literally rewrite this. So it's a half Q1 dot squared plus Q2 dot squared times Q1 squared plus Q2 squared minus V, which is 1 over Q1 squared plus Q2 squared. Okay. L equals T minus V. That's easy. All right, so now we want to find H. So if we want H, we need to know, we need P1 and P2, right? So P1 is given by di L by di Q1 dot. That's the definition of the generalized momentum. All right, so di L by di Q1 dot is going to be Q1 squared plus Q2 squared. And then I have a half Q1 dot squared. That's just simply Q1 dot. All right. Similarly, P2 is given by di L by di Q2 dot. And that's equal to Q1 squared plus Q2 squared times Q2 dot. Okay? And we already know in general that when we convert from the Hamiltonian to the Lagrangian, we're going to need to know the inverse transformation. So we need to know that Q1 dot in terms of P1 is P1 over Q1 squared plus Q2 squared. And Q2 dot is P2 over the same thing, Q1 squared plus Q2 squared. Okay? So we have all the ingredients now, so we can calculate the Hamiltonian. And this is too abstract. We really don't know what T and V really are. So it's a little bit dangerous to just go with the Hamiltonian equals T plus V. It's probably correct, because I don't see any T's anywhere, but maybe it's not going to give the same. So we should apply the Legendre transform. So if you, in the example we just did, if you went and wrote the Hamiltonian equals T plus V, you would have gotten the wrong answer, because we saw that the Hamiltonian wasn't actually equal to the total energy in the previous case. In this case, it's not clear, so let's just be safe. And so to be safe, we use the proper definition. So we want to write that H is equal to the sum over I of Qi dot Pi minus L. So the sum, so now I equals 2, right? Or I goes from 1 to 2. So the first term is P1 times Q1 dot. So that's going to be Q1 squared plus Q2 squared, Q1 dot times Q1 dot, so Q1 dot squared. That's the first term. The second term now, Q2 dot times P2 dot. So P2 dot, or P2, sorry, is Q1 squared plus Q2 squared. And then it's Q2 dot squared. And then minus L. So L is equal to a half Q1 dot squared plus Q2 dot squared times Q1 squared plus Q2 squared, and then plus 1 over Q1 squared plus Q2 squared, right? Now it's just a matter of simplifying this. So the first two terms, right, they both have a Q1 squared plus Q2 squared, so I can factor that, and so I have Q1 squared plus Q2 squared times Q1 dot squared plus Q2 dot squared, minus a half of exactly the same thing. So I'm left with a half of Q1 squared plus Q2 squared times Q1 dot squared plus Q2 dot squared, and then plus 1 over Q1 squared plus Q2 squared. Okay? So that actually does equal T plus V. So in this case, the Hamiltonian really is equal to the total energy. But we don't have the Hamiltonian yet, right? Because remember, the Hamiltonian must depend on only Q's and P's, and here it depends on Q dots. In fact, we haven't put the P's in it. That's why we use our equations that we have above there for the Hamiltonians for Q1 dot and P1 and Q2 dot. So that gives me a half Q1 squared plus Q2 squared. So now Q1 dot squared is P1 squared over Q1 squared plus Q2 squared squared plus P2 squared over Q1 squared plus Q2 squared all squared plus 1 over Q1 squared plus Q2 squared. Okay? Now, the Q1 squared plus Q2 squared is at the front of the kinetic energy term. That cancels the squares at the bottom there. So the first term is a half P1 So it's a half times 1 over Q1 squared plus Q2 squared times P1 squared plus P2 squared. So it's the same denominator as the potential energy term. All right, so I can factor that Q1, Q2 squared out for everybody. And so I get the Hamiltonian is equal to 1 over Q1 squared plus Q2 squared times a half P1 squared plus a half P2 squared plus 1. That plus 1 term matters, right? It's not a constant because it multiplies the 1 over Q1 squared plus Q2 squared at the front. Okay, so we have the Hamiltonian now. That's the Hamiltonian. Now I said we write out the Hamilton-Jacobi equation. So the Hamilton-Jacobi equation, remember, it's given by, we did it just earlier. The Hamilton-Jacobi equation is that you write H as a function of the Qi, the di-s by di-Qi, which we know are the Pi and T, plus di-s by di-T equals to 0. Okay, so I just wrote the Hamiltonian. So the Hamiltonian was 1 over Q1 squared plus Q2 squared. And that multiplied a half. So P1 squared, I replaced that by di-s by di-Q1 squared plus a half di-s by di-Q2 all squared plus 1 equals 0. That's the Hamiltonian part, plus di-s by di-T equals to 0. And that's it. That's the Hamilton-Jacobi equation. You could just give that to a mathematician to solve. Okay. Now, we can go a little bit further. We can note that di-h by di-t is equal to 0. So that means that we can write S to be a function W of the Qi alpha I minus alpha times T. So it's separable. So because it's separable, let's write this out. Let's write the equation for W. Right? So to be really explicit, di-s by di-Q1 is really equal to di-W by di-Q1. Di-s by di-Q2 is going to be equal to di-W by di-Q2. And di-s by di-T is going to be equal to minus alpha. Okay? So if I plug that all in, I get this as an equation for W. So I have 1 over Q1 squared plus Q2 squared times a half di-W by di-Q1 squared plus a half di-W by di-Q2 squared, all squared, plus 1, and then plus di-s by di-T, so minus alpha, and that's equal to 0. what is alpha equal to? Alpha equals total energy T plus V. All right, if I take this equation that I have above and I move alpha to the right, then plus alpha is equal to 1 over Q1 squared times it's basically equal to the Hamiltonian, and we already showed that the Hamiltonian is equal to the total energy, and so alpha really is the total energy. Okay? So that's all I had for today. Any questions? No Ruthians, no. The final exam covers at least all that I've summarized in the introductory lecture today. So the emphasis, for example, would not be to calculus of variations. That was covered in the midterm. But by the time we had the midterm, I think we'd looked at some conservation things, and those weren't included on the midterm, so those could very well be on the final. But the problems on the final are mostly applied, as the examples that we just did. And there's some comprehension required. All right, any more questions? Yes, a lot of comprehension required. Mainly, I want you to look at the review lecture that we did today and make sure you understand the reason for those results physically. And then in terms of the level of difficulty of problems, what we did today was reasonable. And I chose a few problems that highlight some aspects. For example, that energy is not necessarily equal to H, or how you could write out the Hamilton-Jacobi equation. So it's not that difficult to write out, right? It's difficult to solve. Okay, so if that's it for today, thanks everyone. I'll try to get them to convert the video as soon as possible, but I'll make the notes available right away. Thanks everyone.